Hi, today we're going to be looking at semiconductors, and I'm going to start off with talking about the band structure. I'm going to talk about what doping is and how doping can be used to improve the conductance of semiconductors. I'm going to have a look at the two types of semiconductors, the P-type and the N-type, and then I'm going to have a look at the conduction model of semiconductors and how do they actually conduct. So looking at the first things, the band structure. Now we know this, right? This is what an atom looks like. I have the nucleus in the middle and I have the electrons going around it. These electrons are going around in discrete energy levels, right? So this electron can be here, this is one energy level, this is another energy level. The electrons are in discrete energy levels. Now, due to Pauli's exclusion principle, there can be a maximum of one electron in a state. So if I think about it, if this is an atom, then I have an energy level here, and I have an energy level there. This electron 1 is here, this electron 2 is there. If I take two of these atoms that are exactly the same and bring them together, I'll have big E, this is the second one, and the first one. Now Pauli's exclusion principle says that these two electrons cannot be in exactly the same state. So what will happen is, this guy will have to be, let's say, a little bit higher. So he'll be a bit here, and this guy as well will be a little bit higher. So essentially what I'll have is, I'll have two bands there and there. As I keep on adding more and more atoms together, what I'll have is, I'll have more and more bands. So I'll have a band there, and I'll end up having a band there. So essentially what you can see is, rather than having a thin line, now I have a thick band. And these bands can actually be used to explain the conduction of metals. These bands describe how far up can the electrons move. The electrons over here can only move from there to there. The electrons here can only move from there to there. So these bands will tell you the conduction model and tell you how much they can move. And based on these guys, we can have a look at the difference between conductors, insulators, and semiconductors. Now, the lowest band in an insulator or a semiconductor is called the valence, and this is called the conductance. For an electron to conduct, he needs to be here. If the electron is there, then the electron is free to move, it can go and it can conduct. Between the valence band and the conductance band, I have a gap. This gap is called the forbidden gap. The electron cannot be here. It can either be here, in which case it will not conduct, or it can be there, in which case it actually will conduct. As conductor, these two bands overlap, so there's actually no forbidden gap. In a semiconductor, there's a decent sized gap, and in an insulator, this gap is pretty big. And because the gap is pretty big, it's harder for the electrons to conduct. Now, doping. Doping is essentially the process of adding impurities to a semiconductor to improve its conductance. Now, most semiconductors that we'll be looking at will be made from group 4. What I mean by group 4 is that they have 4 electrons in the outermost shell. So if I draw the structure, it will look like this. I'll have the nucleus here. I'll have 1 electron, 2 electrons, 3 electrons, and 4 electrons. I have the other atom there, 1, 2, 3, 4. Another atom there, 1, 2, 3, 4. Now these electrons are all bonded. Alright? These electrons are actually not free to move. They are all actually in the valence band. They're all in a bond. Now, what I can do is I can dope the metal with either a group 5, and in a group 5 I'll have 1 extra electron. So what happens is, I dope it with a group 5 and I get an extra electron over here. Now this electron is not bonded. These electrons are stuck. Alright? This electron, however, is not bonded. So this electron is free to conduct. So this is a group 5. This is called an N-type. Why? Because I've added an extra electron. And because electrons are negative, this has a negative charge, so this is an N-type. The other option I have is I can actually take an electron away. So I can dope it, instead of with a group 5, I can dope it with a group 3. That will be a p-type. And essentially what will happen is there will be a hole here. So you can think about it, there's actually an electron, there's a missing gap over here. The way that this guy will conduct is that because there's a gap, the electron from there is going to jump and try to fill up this gap. In which case, the gap will now be here. And then this electron can jump to fill this up. In which case, the gap will be here, and this is now filled up. In which case, this electron might jump to fill the gap here, and now we have the gap there. So we can actually see that the gap, or the positive hole, is going that way, or the electrons are actually going this way. This is the positive hole. So these are the two ways that you can actually make your semiconductors. An N-type, in which you dope it with a group 5 and you add an extra electron, or a P-type, in which case you dope it with a group 3 and you have one less electron, so you essentially have a positive hole. The conductance model of semiconductors. So this is actually quite important to understand the difference between the two things. What I did in an N-type is that I added an extra electron. Going back to our bands, we have the conductance and we have the valence. In an N-type, that extra electron goes directly into the conductance band. I put an extra electron, it's not tied anywhere, it goes directly into the conductance band, and hence it is able to move. In a P-type, what I actually do is I remove an electron from the valence band. So I actually put a hole in the valence band, and the hole actually moves in the valence band, which then causes the conduction to happen. So there's a difference, and you have to keep that difference in mind. This then can actually be used to make your transistors and your solar cells, and it actually has a lot of applications. That's all for today. Hope you enjoyed that. Thank you.